about the perimeter of figures on a coordinate grid, where we had to find the length of each side and add them all together. Today, we are going to look at area on a coordinate grid. So remind me, what is area? What even is area? The inside. Yeah, it's the space inside any shape. And in fact, it's asking you how many squares fill up a shape. And this one legitimately is full of squares. You could count them and find how many squares fill it up. And that is your area. So it's always measured in units squared because we're finding how many squares fill it up. Now, perimeter, you could do the same thing for any shape. You just had to find the sides and add them. But area, most shapes have a unique formula. So we have to be able to use the correct formula. It's the amount of space inside the boundary of the polygon. That's just any shape. You find the unknown sides by using either the distance formula, or we saw we could create a right triangle off of each side and use the Pythagorean theorem, either way. So let's try to get back in our brains the area formulas for several different polygons, several different shapes. First, we've got square and rectangle are actually the same. How do you find the area of a square or rectangle? Length times width. Yeah, the square is just unique because what's true about its sides? All the same. So we could say it's just side times side, but it's still a length times a width. It's the same thing. So if you can find the length and the width, you just multiply them together, and that's going to give you the amount of space inside, how many squares fill it up. Now a triangle is actually half of a rectangle. And so we kind of start the same, a length times a width, but we have to divide it by 2. On a triangle, we refer to that as the base times the height. Now, on a triangle, the base can be any side, and the height is the distance from the vertex across from your base. So depending on the type of triangle it is, it depends on where your height will be. So on this one, we just put it's a right triangle because it has that right angle. So right triangles are nice because a height has to come down from a vertex to its base and make a right angle. So on a right triangle, you already have that happening. So the base can be the bottom and the height can be the leg, basically, that meets the base at a right angle. So that's always nice. In an acute triangle, we're going to talk about these more in particular soon, but we write acute on this one. That means all angles are smaller than 90. You can pick any side to be the base. Any side can be the base. They chose the bottom for this, so the height has to come from the vertex across from it down to the point that it makes a right angle. We could have chosen this side to be the base, and we would have to figure out where that side would end up, or that segment from the vertex, to make a right angle. So any side can be the base. The height has to go from the opposite vertex down to it and make a right angle. Now this one, it's obtuse. What does it mean to be obtuse? Did you remember that? Yeah, there's an angle in there greater than 90. And if it's obtuse, whatever side you pick to be the base, the height might actually have to go outside of it, because if I pick the bottom side and I have to use the vertex across from it, there's nowhere I can draw a line down that would be a right angle. So we kind of have to extend out the base so that you can go straight down from a vertex to create the height. So each triangle is a little bit unique. We'll look at the best option to use the base and to get an easy height to find it. We could use this side as the base, and it would be easier to head right down and create a right angle. It just depends on where it is. So that's our triangles. You do base times height, divide it by 2. You can look at it as base times height divided by 2, or base times height times a half. It's the same thing. But you just have to know base and height. The height has to come down from a vertex and make a right angle. Okay, long story on that. The next one is a parallelogram. It's like a rectangle, but as you can see, it's just kind of squished over. It's been squished over. Parallelogram. What's true about its sides? Any ideas? They're parallel, top and bottom are parallel. Same with rectangles. Rectangles are parallelograms, they truly are, but they're a special one because all their angles are right angles, keeping them straight. But most parallelograms are not. So opposite sides are parallel and they're the same length. You still do a length times a width, but we have to call it base times a height again. The height has to go from the base to the opposite side, and you just draw on your notes, it's gotta make a right angle. It does have to make a right angle. So you pick the best option for the base on a parallelogram is to use one of the very horizontal sides or vertical, we'll see both. Choose one of those and just go from its corner to the opposite side perfectly straight so that you can make a right angle. It's gotta be perpendicular. Base times height. The height has to make a right angle with the opposite side. Now, trapezoid is probably not one we use very often. It's unique and its formula is unique. In a trapezoid, you have two sides across from each other that are parallel. They call those the bases of your trapezoid. And then, of course, it does have a height similar to the parallelogram. It's got to come down and make a right angle from one of those parallel sides. It has to make a right angle. So the area, to find that area, it's kind of like you have two triangles in there and a square or rectangle in there. So they come up with a formula to account for all of that. You have to add the two bases together, however long base 1 and base 2 are the parallel sides. In fact, we write parallel sides by that. When we talk about bases of a trapezoid, it's the parallel sides. You have to add those, then times it to the height, and divide by 2, or times by a half. So that one is unique. We don't use it as often as the others, but we do not need to know its formula. So we've got them all. You've got them in your notes. Let's use this one. So you're going to be asked to graph a figure in the grid. So let's go ahead and graph this. 1, 3 is D. I would label it. Again, if you want to write the coordinates, you can. You might find that you don't need to, and that's okay. But it's a good idea to know where each point is and which ones we're working with. And then -4, -3. So we've got triangle, DEF. Do your best connecting. Now on a triangle, you can choose any side to be the base. But looking at this one, what side do you think might be the easiest base to use? Yeah, F and E. F and E. If there is a perfectly horizontal or if there's a perfectly horizontal or vertical side, that's going to be the easiest route because it's going to help us in a couple different ways. Right? If we let this guy be the base, let's just put a B there, then the height has to come from the vertex across from it straight down and make a right angle. So could you easily find the length of FE? Do you even need to use the distance formula? No, when they're straight, you can count them. So that's why it's a good option to pick sides that are straight if you have that choice. So how long is the base? 8. And then the height is also vertical, and so you can count it. So if you can choose sides that are given to you, perfectly horizontal or vertical, it's going to save you a ton of time. So area for a triangle. A couple ways you can think of it. It's base times height divided by 2, or a half times base times height. It's the same thing. So what's 6 times 8? 48 divided by 2, 24. So the area of this triangle, and we're going to say just units squared. We need to remember that area is always measured in any kind of unit squared, because it's how many squares fit inside. So sometimes it can be fairly easy. Let's take a look at this trapezoid. Now, I obviously went too fast making this note packet, so I need you to change these coordinates so that it's going to actually work out. So will you change your coordinates to match mine? I went too fast and copied the wrong coordinates, obviously, because it did not work out as it should. It wasn't even a true trapezoid because there weren't parallel sides with the coordinates you had. So change them, match them to these, so that we have the actual true parallelogram, or not parallelogram, trapezoid coordinates. Change those. So we do have to have true parallel sides to be a trapezoid. The other coordinates did not make that happen. Okay, so while you're changing it and graphing it, let me just remind you the formula for area of a trapezoid. We have to do half bases added times the height. So we gotta find the bases and we gotta find the height. So we gotta find three things. Now with this particular trapezoid, did anything end up perfectly horizontal or vertical? No. So we have some work ahead of us. So we gotta find the length of each base. The bases are the sides that are parallel, the two that are running the same direction with the same slope. So if you want to use the distance formula, you can. I think it's probably easiest just to make that right triangle off of that side and do the Pythagorean theorem. That's probably the quickest, fastest route. Is how long is the vertical base? Or side, sorry. It's 4. How long is the horizontal? It's also 4. So we can do leg squared plus leg squared equals that hypotenuse squared. That will give us the length of the longer base. So 16 plus 16, 16 and 16, 32. Square root it. Let's go to the nearest hundredth today just to get a little more accuracy. Okay, what is the square root of 32? To the nearest hundredth. Let's go 100. 5.66. Okay, so there's that one. That's one base. Let's do the other base. Same thing. You can just connect its ends into a right triangle. How long are each of its legs? 2. So 2 squared plus 2 squared equals the hypotenuse squared. 4 and 4, which combine to be 8. Square root that. What is the square root of 8? 2.83. 2.83. So there's our second base. Now we need the height. The height has to go from the base, one base, to the opposite base at a right angle. So usually it's easiest to take the smaller base and just start on a vertex and go straight down to the opposite side. And either one is going to be the same length from either vertex. So we've got this guy right here that we've got to find its length. Now you could do the distance formula. You have this point and now you could write down this point and do the distance formula. But if you can make your eyes see the triangle, just if you focus on that height, just that height, not looking at the trapezoid, you can connect its ends in a right triangle. If you can make your brain see it, sometimes it takes a second to not focus on the trapezoid part. So my eyes keep looking on this triangle piece. But if you connect, you got to connect end to end. Everybody okay doing that? How long are its sides? 2.83. It's the same. 2 and 2, right? It's the same as this one. It ended up being the same length. That happens once in a while. Not every time, but it did. It was a 2 squared and a 2 squared, being the square root of 8. So we've already got that one. We've got the 2.83. Okay, now that we have all three of them, let's put them in the formula. We got to do half times the base plus the other base and times our height of 2.83. So what do you think we do first? Parentheses. Yeah, we got to add those bases. Yes, you have to do the parentheses first. What did you get when you added them? 8.49. And then you can just start left to right and do the multiplication. Or you can times these two and then divide by 2. It's up to you. It doesn't matter. Just go times and divide by 2, or just do a half times the other 2. Let's go nearest hundredth again. What's the area? I guess I should say area. What did everyone get? Everybody getting a 12?
Yeah.
0.01, did I do that right?
Yeah.
Okay, and units squared. Units squared. Okay, so trapezoids probably take the most time, but I think most of ours do have a vertical side or a horizontal side that we can just count and go from there. So I wanted to show you one that probably takes the most effort. It's doable, just takes time. Okay, this last one, parallelogram. I think I need to change these two because I didn't give you a good enough graph. I told you I was going too fast, you guys. Trying to get the notes ready. Change your 6s, they just need to be 5s to fit on our graph. Change your 6s to be 5. I think D's fine. Did that change at all? -3, 2 for you? Yeah, we're just gonna squish it in to fit on this graph that I put on here. That teaches me to check things. 5, 2. We just needed it to fit on our graph nice, so we didn't have to estimate off of the dates. -5. And then -6.
So the bottom of the line.
Sorry, thank you. Okay, well, that's not connecting correctly. Alrighty, there we go. There's our parallelogram. Parallelogram. So you have to do a base times a height. The height does have to make a right angle. If you have an option, I would let the base be a straight side. Do we have some straight sides? Hallelujah, we do. Top or bottom can be the base. How long is the base? 1, 2, 3, 4, 5, 6, 7, 8. And then your height just has to go from the base to the other side. You can go from the corner, from a vertex, down to the other side. It could technically just go from base to base as long as you're creating a right angle. It just has to create a right angle as it meets the other side. So either way, and nice, they're vertical, so we can count them. How long's the height? 7, so there we are. So the area for a parallelogram is just base times height. Nice enough, we didn't have to use any distance formula or Pythagorean theorem. What is 8 times 7? 56 units squared. So the key is if your figure has some perfectly vertical or horizontal, and it's part of what you need,